So in this video, I'm going to walk through an example that is in the textbook, but it's one of those examples that I think is really instructional and really confusing. So the example we're going to deal with here is sort of deriving the rocket equation. And if you really understand what's going on in the derivation of the rocket equation, you're really getting a lot of the key ideas of this module around conservation of momentum. So let me first sort of set up the idea of this a little bit. So the idea is that we have this rocket, right? So this is a rocket. And the way that a rocket works is it actually burns fuel, and in burning the fuel expels hot gases out of the back of the rocket. And if you think about this from a sort of system boundary perspective and sort of imagine a system boundary there, as the rocket expels hot gases, you have molecules that are crossing the system boundary going that way. In other words, they are carrying momentum that's going to the left, and they are carrying that momentum out of the system, so they are subtracting momentum in this direction, or another way of saying that is that they are adding momentum in this direction, so that's what pushes the rocket forward. That's one way of thinking about the way a rocket works, is from a sort of momentum conservation perspective, that each of these molecules that leaves the system carries away momentum in one direction, which in turn implies that the remaining momentum must change in the other direction. Of course, another way of thinking about it is from a force perspective. You could equally say, well, in order for the rocket to expel that little bit of mass, it has to push on that bit of mass. It applies a force to the mass. Therefore, the mass must apply an equal and opposite force to the rocket, and that's what accelerates the rocket forward. Both of those are legitimate framings for talking about how this works. Now, the question that we're interested in here is, how does this rocket actually move, or what are the equations of motion for the rocket? And I will note that this is something that you're really asked to deal with in great detail on the diagnostic, so this clip will help you work on that diagnostic. In order to get at that, the first thing we have to do is define what our state variables are, how we're going to think about this. And so I'm going to say that the rocket has a position, right? The rocket's position is given by r vector sub r. That in turn implies that the rocket also has a velocity, which is v sub r. The rocket has a mass, m sub r, and note that the mass of the rocket changes in time, right? That mass is going to be decreasing as the rocket burns that fuel and expels fuel. Finally, one of the things that's important about a rocket is the rocket actually has to expel that fuel, and typically the way that you think about that is you talk about there being an exhaust velocity. So I'm going to call that v sub e, which is the exhaust velocity. I want to take a second to talk about what we mean by the exhaust velocity, because it's a little bit of a confusing concept. And it's mostly confusing because it requires that you think about reference frames. So one reference frame we could think about is the reference frame where you're actually an observer who's sitting inside the rocket, and you're looking at a little bit of exhaust that is flying out of the rocket. Okay? From the reference frame of an observer in the rocket, they would say there's a little piece of mass. I'm going to call that dm, that bit of mass. And that bit of mass is leaving the rocket, and the velocity of that bit of mass is v sub e, right? So the exhaust velocity is the velocity as measured by someone in the rocket's frame of reference. They're sitting in the rocket and they're saying the exhaust is leaving this rocket at 3,000 meters per second, or whatever the exhaust velocity is. Now notice that means that if you actually think about this from an observer who's on the ground watching this rocket fly by, right, the observer on the ground would say, well, what I see is a rocket that's flying forward at a velocity v sub r, and I see exhaust coming out of that rocket, and that exhaust actually has a velocity that is v sub r plus v sub e, right? So the sort of exhaust velocity that an observer on the ground sees is actually has to be offset by what the velocity of the rocket is, right? So it's actually possible that from an observer's perspective on the ground, this exhaust could actually be going forward. It could just be going forward at a lower speed than the rocket was going forward at. Okay, so when we say exhaust velocity, we mean exhaust velocity in the reference frame of the rocket. Okay, so having set that up, let's now go on to actually think about how things are going to change in this. And I'm going to approach this rather than trying to write differential equations right away. I just want to think about a time and then a time a little while later. So I'll ask the question first, what does the mass of the rocket look like at time t plus dt, right? So if I know what the mass of the rocket is at time t, do I know what it's going to be at the time t plus delta t? And the answer to that is, well, the mass of the rocket at time t plus dt is simply the mass of the rocket at time t minus whatever little chunk of mass dm, we talked about back here, minus that little chunk of mass that got thrown out. In other words, I can go from this to a differential equation right away. dm sub r by dt is simply negative dm by dt, right? So when we talk about dm, we're talking about the mass that's leaving, and since that mass is leaving, the rocket's mass is dropping by a rate that's determined by how fast that mass is leaving the system. The second thing we could actually think about is how is the momentum of this system changing? So what's the momentum of the system at time t plus dt? Well, if we go back up to our system diagram, at time t, we have some momentum of the system. And during the time dt, what happens is this little chunk of mass dm leaves the system. And it leaves the system, if we're looking at this from the perspective of an observer on the ground, that chunk of mass dm leaves the system with a velocity of v sub r plus v sub e. So actually the new momentum of the system will be the old momentum of the system minus the amount of momentum that's left the system, right? And the momentum that's left the system is d sub m, or dm, times the velocity of the exhaust relative to the velocity of the rocket, right? In other words, minus dm times v sub e plus v sub r, right? Remember that v sub e is the velocity of the exhaust relative to the rocket. Okay, well, now we can step back a little bit and think about what is this momentum? Or we can, well, let's turn this into a differential equation first. So we'll simply divide through by dt, and we'll bring this over to the other side. So we're going to have the new momentum of the system minus the old momentum of the system, or dp system by dt, right? The time rate of change of the momentum of the system is going to be minus dm by dt times v sub e plus v sub r. In other words, the momentum of the system is changing, and it's changing due to momentum leaving the system, and the amount of momentum that's leaving the system per unit time is dm by dt times v sub e plus v sub r, or dm by dt times the velocity of that chunk, that little differential chunk that's leaving the system. Okay, now at this point, we could do a couple of things. One is we'd like to actually reframe this in terms of our state variables, and you'll recall our state variables here are the mass of the rocket and the velocity of the rocket, and of course the position of the rocket. So dm by dt we already know is the negative of the time rate of change in the mass of the rocket. So we can rewrite this as dm sub r by dt with a positive sign times the velocity of the rocket plus the velocity of the exhaust relative to the rocket plus the velocity of the rocket. In other words, the velocity of the exhaust as measured by an observer. And the other thing that the observer would say is that, well, the time rate of change of the momentum of the system, well, the momentum of the system is given by the mass of the rocket times whatever the velocity of the rocket is. So if I take a time derivative of that, I've actually got two things that are changing in that time derivative. One is the mass of the rocket is changing, and the other is the velocity of the rocket is changing, right? So I get d by dt of m sub r times v sub r, which in turn is m sub r dot, or dm sub r by dt. That's what I actually write, dm sub r by dt. dm sub r by dt times v sub r plus m sub r dv sub r by dt. Right? This is just using product rule here for obtaining this equation. Okay? And at this point, I can now say, well, aha, look, this term here is the same as this term. And so I would be able to collect some terms and get the expression that m sub r times dv sub r by dt is d m sub r by dt times v sub e. Okay. Now we could take a minute to think about that equation and see if that actually makes any sense. So one of the things we can see in this equation is that on the left hand, let's think about signs. And we'll think about signs first on the right hand side. So dm sub r by dt is going to be a negative quantity, right? The mass of the rocket is dropping in time, so this is going to be this derivative of the mass is going to be negative. V sub e is the velocity of the exhaust relative to the rocket, and if we're defining things with a sort of positive, say this is the positive x direction, V sub e actually is in the negative I hat direction. So I'll say for this sort of case of travel in the x direction, V sub e is actually in the negative direction as well. Okay? So this left-hand side, we have two negative quantities times each other, so this gives me a positive quantity. Then if we think over on the right-hand side, when we look at that, clearly m sub r is always positive. That's simply what the mass of the rocket is. So dv sub r by dt is going to be positive. In other words, there will be a positive acceleration to the right due to the fact that we're expelling mass to the left. And the other thing that you can observe here is that, in fact, the amount of acceleration you get depends on a number of things. One of the things it depends on is what the mass is. Clearly, if the mass is higher, you get less acceleration. But there are two things that can make that bigger. One is expelling more mass, in other words, increasing the rate of mass expulsion, increasing the amount of fuel you're burning. And the other thing that you could do to increase that acceleration is to increase the speed with which that fuel is leaving the system, so increase the exhaust velocity. And so when you think about designing a rocket, there are two sort of knobs you might want to turn. One knob that you might want to turn is sort of how big is your nozzle, which will determine, or how big are the pipes, right? How much mass you're going to be able to burn per unit time. And the other is, what type of fuel is it, and how fast does does each particle that you expel out of the system actually leave the system. And so this is a really nice example of this sort of idea that starts with asking the question, how much momentum is there in the system and what momentum is flowing across the system boundary, and taking that sort of flow of momentum and translating that flow of momentum into a differential equation that talks about how much momentum is leaving the system, right? Well, we know how much momentum is leaving the system, to finally be able to write a differential equation that describes how the actual velocity changes in time, in other words, what the acceleration is. Now, one of the things you might think about on this, and you're going to have to think about as you think about the diagnostic, is, okay, we've drawn this system diagram in this case where the only flow of momentum is due to mass leaving the system carrying momentum. How do these equations change in the case where you've also got other interactions? In other words, for example, what would happen if I added a gravitational interaction, so that now I also have a force of m sub r times g acting here? How is that going to play into these differential equations? And that's something you'll want to think about on this diagnostic.